So what we're going to do is we're going to use the Biot-Savart Law to talk about how to determine the magnetic field at point P due to current carrying wires. Now, let's start by backing up and remembering how we basically used Coulombs Law to figure out what the electric field was from a continuous distribution of charge. So we said, well, the electric field contribution due to some tiny little charge element dq was given by this expression. So we said there's going to be some tiny little contribution to the electric field that we're going to call dE. We've got k dq over r squared, and then there's this r hat term because, again, we're going to care about the direction since this is a vector. And then to calculate the electric field over our continuous charge distribution, we just need to add this up over all of our little possible charge elements. So you can see that in the picture here we've got an element dq that's going to contribute a dE in this direction, but over here there's a different dq that's going to contribute a different dE. There's another dq that's going to contribute another dE. And so all we're going to do is just add up over our entire continuous distribution all our little contributions from the charge elements dq. Well, we're going to play a very similar game, and then the k here, let's remember that our k in this Coulombs law is 1 over 4 pi epsilon naught, and then epsilon naught has a value of 8.85 times 10 to the minus 12. Here are its units, and this is known as the permittivity constant. So there's a fundamental universal constant that's sort of hidden in this, this version of Coulombs law that we're adding up to find the electric field. Now we're going to play a very similar game about the magnetic field to figure out what the magnetic field is. A couple of important differences. So here's the Biot-Savart law. What the Biot-Savart law tells us is that the magnetic field contribution due to some tiny little current element, and so we've got our little current element of I dl. So notice dl is just a length, and so I'm taking my current times a length to get my current element. Dl is a vector. It's a vector that points in the direction that the current is flowing. So to calculate the contribution to the magnetic field due to some little choice of current element, I use this expression. So you'll notice that instead of k out front, I've got mu naught over 4 pi. Again, because this is a magnetic thing rather than an electric thing, I've got that cross product that we ran across when we were talking about the magnetic force. And then again, this still ends up being an inverse square law. I've got 1 over r squared sitting here. So what we're going to do is we're going to have some tiny little chunk of current. So here's current flowing in our wire. We're going to pick some tiny little element dl. So we'll have our IDL. R hat is going to point from our little current element to the point P where we're interested in the magnetic field. And again, we'll see that there's a right-hand rule that will help us figure out the direction at which this is going to point. But here, dB will point into the page. So one thing that we see is, again, if I'm over here and dB is pointing into the page, that part of what this cross product means is that the magnetic field is actually going to circle around the source current. So the source current over here, the magnetic field is actually going to circle around that. That's entirely due to this cross product. Right? So we know that since this cross product tells us that our magnetic field contribution has to be perpendicular to both the current element and r hat, and again, both of those in this case happen to lie in the plane, the plane of the page here, which means that the magnetic field contribution is going to point into or out of the page. It happens to be into the page in this case. And so when you sort of think about that moving around your wire, what that tells you is that the magnetic field actually circles around the wire. Again, there's a really important fundamental universal constant here. Mu naught happens to be 4 pi times 10 to the minus 7, and it has units of Tesla meters per amps. And this is what's known as the permeability constant. So epsilon naught is the permittivity constant, mu naught is the permeability constant. and we'll come back to the importance that these two things play, particularly when we start talking about electromagnetic waves. So what do we do to get the magnetic field? Well, basically we do what we did with the electric field. We need to sum up, so integrate over all of our little contributions from the wire. So if I've got some wire that's flowing like, where the current is flowing like this, I've got contributions from all the way down here, contributions to all the way up here. Okay? So I need to just add up all those contributions from my various little current elements. So I'll do it with an integral. Again, the mu naught over 4 pi, that just comes out. And so I'm left with an integral of this piece. And so what we'll see is that there's actually sort of a process that we can use to deal with how do you convert this into something that's actually doable as an integral. So what's that process? So how do we use the Biot-Savart Law? Well, so what we're going to do is we're going to say, well, we know that what Biot-Savart tells us is that our little contribution to the magnetic field is given by this expression. But we know that the magnitude of this, right, so the magnitude of our little contribution, dB, that's just going to be mu naught over 4 pi, that doesn't change. This cross product tells me the magnitude of this vector, so that's IDL. The magnitude of this vector, well, this is r hat, it has magnitude of 1, times the sine of the angle between them, and then I've still got my over r squared term. So what we're going to do is we're basically going to, same way we always do, we're going to draw a sketch, then we'll pick a current element, we'll draw in r hat, and we'll use a right-hand rule to determine the direction of dB. In this case, again, our right-hand rule is going to tell us that our little contribution to the magnetic field is going to point into the page. Right? And what we'll recognize is that pick any other current elements you want along this wire, and that's going to be true at all points, that the contribution from any of these current elements is all going to point into the page. So what that means is we really just have a single component, right? If we want to think of this as x left and right, y up and down, z into and out of the page, this really just has, our magnetic field here really just has a z component. The x and y component is 0. So the next thing we'll do is we'll say, well, we need to determine dl. And again, that's going to be well, are you integrating in y? Are you integrating in x? Are you integrating in z? Are you integrating around some circle? We'll need to figure out what r is, so what's the distance from my current element to the point P, and we'll need to figure out this sine phi term. So again, our angle phi is the angle between our current element and r hat. In this case, this happens to be phi, so we'll need to use the geometry of the problem to figure out what sine phi is. We'll plug all that in, and that'll give us dB, our little contribution to the magnetic field, in terms of the variables within our problem, and so then we can just plug that in and integrate. So this is the process that we're going to use to use the Biot-Savart Law. And the next video that you guys will watch, we'll start by reviewing this real quickly, and then we'll look at a couple of examples.